For the second part of our introduction to hypothesis testing, we're going to walk through an entire hypothesis test without any formulas and without any calculators. I just want you to understand the logic behind what it is hypothesis testing is built on. If you remember from the last video, part 1, intro, we learned how to take a sentence or a claim and convert it into two hypotheses. So let's read this. This claim says the average age of all Butte College students is more than 24 years. Well, we know that there's two hypotheses, the null and the alternative. So let's call out the important words here. Now, I already underlined the word all to emphasize this is always referring to an entire population. Some other key words and phrases. The word average tells us we're going to use the symbol mu. And the phrase more than 24 years tells me that's not saying equals. So they're describing the alternative hypothesis here. So let's convert it into a mathematical expression. Average mu more than greater than 24. So what's the complement of this? What would this be? We would normally say mu is less than or equal to 24. Here's where I'm going to start amending that pure complement. If you said less than or equal to, that would be perfect. But the main part of that operation is the term equals. If you remember in my first video, the most important thing to recognize is the null always gets the equal sign. And you'll notice this in your homework problems, that the null always just has the equal sign. So, again, it might bother you a little bit that we don't have a less than sign, but let me tell you why it doesn't matter. Remember, the null is what we call the status quo. It's what we kind of already believe. So this is, I'll put next to this, this is what we currently believe is true. But this claim is that someone thinks it's actually more than that. There is no concern that it's going to be less than that. So that's not really a part of this. So this is what we're trying to convince people of. Is it possible that the average age is actually more than 24? So this is what we have evidence for. We'll never have evidence for the null. We just assume it's true. We're trying to convince you, me, others, that the alternative is what we should believe in. Okay, so here's the next move, is once we've set this up, we have to go get some evidence. And so this will either be provided, you'll be given a list, but the bottom line, let's make up something for this conversation. Let's say we got a sample of some students and we ended up with a sample mean age of 26 years old. So, before we do anything else, would you agree we have evidence for the alternative? Of course we do. 26 is greater than 24. So, whatever this claim is, my data so far supports it. But, like with anything, is that enough data to convince us to switch? And here's where we go to the next phase. I have two different bell-shaped curve here. There's not actually two when you do a true hypothesis test. There's just one. But I'm going to show you two different possible scenarios that could happen next. First of all, anytime we have this bell-shaped curve, because we believe the null is true, the null gets center stage. Whatever number you put in as the null, always put that number smack dab in the middle in that number line. And here's what we don't know. My evidence, 26, clearly is greater than 24, but what I don't know is that evidence somewhere about right here, or could it be somewhere way down here? We honestly don't know All we know is 26 is bigger than 24. Is 26 actually pretty close to it, or is it pretty far away? One thing we're pretty good at is finding the area under a bell-shaped curve. Now, depending on where you put that evidence, that 26, that shaded tail is either really big or really small. So I'm going to ask you a question right now and ask you to either pause the video or think quickly about your answer. What we're trying to determine is my evidence of 26 years. Is that, I already know it's greater than 24, but is that strong enough evidence to switch to the alternative? So tell me, which picture does it seem like 26 is indicating that it's strong evidence to switch to the alternative? And which picture is telling us it's some evidence, but we should stay with the null? Well, here's my answer. If my actual evidence is so far away from the mean that it's clearly not an accident that this could have happened, this is the time that we would switch to the alternative, because that evidence is very strong that it couldn't be 24. Or on the other hand, in this image, if 26 is actually kind of close to 24, we would probably be better off staying with the null. And this is how we make, in general, how do you know which hypothesis do we decide on? Do we end up with the null, or do we end up with the alternative? It depends on where that evidence falls. Now, because we don't know really where to put it, we have to depend on the area of that tail, which is something we know how to find. I think you'd all agree that the area of this tail is big area, where on this one, this is a small area. And this is how we're going to make our final decision. It turns out the area under these bell-shaped curves we're going to talk about has a name. So the area under the curve when doing a hypothesis test is called the p-value. And here's the two decisions you have to make. When the p-value is big, like in this image, we stick with the null. And the way we say that is we say fail to reject the null. When the p-value is small, like in this image, that's when we want to switch to the alternative. And the phrase we'll say there is reject the null. Now, one vague question we haven't answered yet is, I know what big looks like versus small if you give me two options, but how do we know when the area actually goes from big to being small? And there is a number that's going to determine this. This is called the alpha level. That symbol I just drew is an actual Greek letter, alpha. And we typically will give it a cutoff. The most common being 0.05. In other words, if the p-value is bigger than 0.05, it's considered big. If the p-value comes in under 0.05, we consider it small. 0.05 is the most common, but it could be others. So just read your homework problem. Other common ones could be 0.01 or even 0.10, but 0.05 tends to be the most common one. All right, I think we've got it. In the next videos, we're going to look at a number of examples, and that's where we're going to bring our calculator in, and it's going to help us turn data into a p-value, which is going to help us make our hypothesis test get concluded.